Hello, my name is Valor and I was a part of AJ's Deep group for the 2025 to 2026 Deep year. And for our project, we simulated the quantum tunneling on a computer. So in order to simulate quantum tunneling, we need to simulate the Schrödinger equation. However, it's noticeable that the Schrödinger equation is a partial differential equation, which is continuous, but computers don't do very well with continuous means. So we have to find a way to discretize it. In order to do this, we used the Crank-Nicolson algorithm and then transformed it into a matrix equation, which we could solve. So in the code here, we start by initializing several initial parameters, which we're going to use in the code, and then some parameters for the barrier, which we're going to see the particle tunnel through. We begin by initializing our wave packet as a Gaussian distribution at the center of our box, and then construct two matrices, B, which represents our explicit terms, and A, which represents our implicit terms, so that we can solve for our wave function psi at every single time step. So what we're what we're doing is, as you can see on the paper to the right here, we are taking the equation and we are doing a finite difference approximation, and so we can get with a very good estimate of what the equation's true behavior will look like. So we take the equation, we apply a Crank-Nicolson approximation, we break it up into discrete parts, and then break up the Hamiltonian into discrete parts, and for this, as well as the second order partial. And then we get this finite difference equation over here. After this, we notice that, as I said here, we can write this as a matrix equation where we have a the explicit matrix here, B, and the implicit matrix here, A. So we're initializing our explicit matrix here, B, in this code, and our implicit matrix A here. We then notice that this is in a tridiagonal form, so we can apply the Thomas solve algorithm, which reduces our computational complexity significantly. Doing that allows us to find the value of psi at every time step, which we do here via the Thomas solve algorithm. Doing this allows us to find psi at a particular time step, and then we just loop through the algorithm over and over and over again to watch our wave function evolve over time. Now, as you can clearly see in the code, a lot of the matrix computations, it's not directly handled by me. It's in fact handled by this eigen package here, which has been extraordinarily helpful. Now, after we have computed psi at every time step, we can watch it evolve here. Oop, there we go. As you can see, when it hits the barrier, the probability starts spiking, as should be expected. And you can see, if I scroll down here, this little trailing edge, which represents the incredibly small probability of you being able to find the particle just appearing on the other side of the barrier. Thank you.